Okay, this last lesson on this chapter on trigonometry is a little bit more about solving trigonometric equations and looking at some slightly more tricky ones. Now, if I've got an equation like this, cos 3 theta equals 0.766 between 0 and 360, what this means, hopefully you'll recall from when we did graphs and transformations in chapter 4, this is basically taking the graph of cos theta and turning it into cos 3 theta. So we're going from f of theta in this case, and we are transforming it into f of 3 theta. And hopefully you'll recall that that is a squash horizontally of 3. Okay, so that means instead of my graph looking like the cos graph between 0 and 360, it's going to be squashed 3 times horizontally. So it's going to look more like this. 1, 2, 3 between 0 and 360. So I've got 3 waves instead of 1. So this is obviously going to give me much more solutions between 0 and 360. Okay, if this is 360 normally equals 0.766, I'd normally get 2. Now I'm going to get 1, 2, 3, 4, 5, 6 solutions instead. I have 3 times as many solutions. So there's a few different ways we can solve these. We can either solve it as we would normally and then think about how the symmetries have changed. So rather than doing 360 minus, I'm going to have to do 120 minus my answer. And instead of adding on 360 to find the next cycle, I'm going to have to add on 120 because the cycle is now much shorter. It no longer has a period of 360. It has a period of 120. And you can use that as a method, but I tend to find that that leads to slightly more mistakes than the method I'm going to show you. I'm going to show you how to do it with a substitution. And this is a useful method for when you get a slightly more tricky one that isn't just 3. Maybe it's some awkward fraction or something like that, which makes it a bit harder to think about the symmetries. So what we're going to do is we're going to make a substitution. We're going to let 3 theta equal a new variable, which I'm going to call phi. So now my question becomes cos phi equals 0.766. And we've also got to change the limits. So if 3 theta is phi, then that means that theta would be phi divided by 3. So that means my limits, instead of theta, I can write phi divided by 3. But I don't want my limits to talk about phi divided by 3. I just want them to talk about phi. So I'm going to times them all by 3. So 360 times 3 is 1080. And now I've got a new problem to solve. I've got these new limits and this new question. However, it is a much easier question to solve. So I'm going to find my first answer by doing inverse cos of 0.766, which gives me 40. And then I'm going to go through and find my next solution. So I'm going to do 360 minus that, which is obviously 320. And then I'm going to find my next pairs by adding on 360. So that'd be 400. 320 plus 360, 680. Now I'm going to take that pair. Remember, I'm looking up to 1080. So there's going to be a lot of solutions. 400 plus 360, 760. And 680 plus 360, 1040. And I think any higher than that, I'm going to overshoot my limit. So those are my 6 solutions, which is what we agreed that we would come up with. But now I just need to convert them back into theta. And remember that theta was phi divided by 3. So I just need to take these answers and divide them all by 3. So 40 over 3 is 13.3. 320 over 3 is 106.7. 400 over 3, 133.3. 680 over 3, 226.7. 760 over 3, 253.3. And then last of all, 1040 divided by 3, which is 346.7. Okay, so it's a little bit long-winded sometimes, but it tends to be quite methodical and students tend to be quite successful with using this method. And you'll notice that it sorts out your limits for you. Because we've done this algebraic substitution, we've created a much easier question And then we've changed our limits to talk about this new variable. Find your solutions to your new question, and then just convert it back using what you used before. Okay, and notice that these answers are all within my original limit of 0 to 360. Let's have a go at another one. So now I've got 2 sine 2 theta equals cos 2 theta. Well, the first thing I'm going to need to do here is try and get it all in terms of one function, because I've got sine and cos here. So I think I'm going to divide both sides by cos 2 theta, and then use one of my identities. So that's now going to give me 2 tan 2 theta equals 1. So then tan 2 theta equals 1/2 between 0 and 360. Okay. Now I'm going to make a substitution. I'm going to let 2 theta equal phi. So my new question is tan phi equals 1/2. I need to change my limits as well. So theta is phi over 2, and I can swap that in instead of theta. Times it all by 2. So I have 720. So then this is my new question. Tan phi equals 1/2. Solve that between 0 and 720. Okay, let's do that now then. So inverse tan of 1/2 is 26.6. And remember, for tan, to get multiple solutions, we just add on 180. So that's going to be 206.6, 386.6, 566.6, and then after that it would be above the limit. The next one's 746, so that's far beyond our limit. Okay, now I need to just swap it back to talk about theta, and theta was equal to phi over 2. So I just need to half all these values. So we've got 13.3, 103.3, what's this, 193.3, and 283.3. Okay, and those would be all my solutions. And again, you can see they're within our original limit. If you wanted to do it without doing that, like I talked about before, consider what the graph of tan theta looks like. So normally it looks like this, where this is 180 here. There's another asymptote here, and this is 360. So normally it's periodic of 180. If it's tan 2 theta, that means it's been squashed horizontally by 2. So instead of having a period of 180, it would have a period of 90. It would be twice as frequent. So rather than adding on 180 each time, you would add on 90 each time, and you could find your multiple solutions that way. That is an alternative method that might be quicker sometimes. Okay, here's another example. This has actually got 2 transformations that have happened. So you've got 2x plus 60 in there. This is a translation left by 60. That's what the plus 60 bit does. And it's been squashed by 2 horizontally. So you've got 2 different transformations which have happened, which makes it a bit more tricky to think about the symmetries. So I'm just going to go for substitution here, I think. So I'm going to let 2x plus 60 equal phi. So my new question is sine phi equals 0.3. I need to change my limits as well. So let's rearrange this for x. So that means phi minus 60 over 2 equals x. So in my limits, I can replace this with 0. Instead of x, I can write phi minus 60 over 2, and then 180. And now what I need to do is I need to times it all by 2 and then add 60. So this is going to become 60. This will become phi 180 times 2, and then add 60. So that'd be 420. So this is my new question. Solve sine phi between 60 and 420. Okay. Let's just sketch what that would look like roughly. So there's up to 360. I'm just going to draw another wave in here, just because we've got to go a bit further. Okay, and we're solving equals 0.3. So we're going to get that one, and maybe this one, but depending on what value it is, if it is actually less or more than 420, we will see. So inverse sine of 0.3. My first solution is 17.5. The next one I can get by doing 180 minus my answer, just using those normal symmetry rules we learned a couple of lessons ago. So there's the first two. Now remember, to get to the next one, I could add 360. So 360 plus 17.5 is 377.5. So yeah, that's in my limit. Let's check the other one, 162.5 plus 360. That would give me 522. So the next one wouldn't be in my limit. So those are my three solutions. Now we've just got to convert them back. So we wrote earlier that x was 5 minus 60 over 2. So that's what I've got to do to each of these values. So x is going to be 17.5 minus 60 divided by 2, which gives me, oh wait, actually that's 17.5 wouldn't count, sorry, because my limit was above 60. So actually we don't need to worry about that first one. I spotted that because I realized that it came out with minus 21, which is obviously not in my original limit. So you've actually only got two answers. 162.5 though, minus 60 divided by 2 is 51.3. And the other one, 377.5 minus 60 divided by 2, 158.8. And those would be my two answers. So it's quite methodical using this substitution method. Okay, if you want to practice ones that are a bit like that, so those transformed trig equations, then have a look at exercise 10e in the book. Okay, I've got a couple of extra questions here to look at that involve quadratics. This first one, well, it's just a regular quadratic. It just happens to have cos squared involved. So you can solve this quadratic however you want. You could factorize it. You could use a formula. I am just going to use my calculator, I'm afraid. But that's fine. You can do that in the exam unless it says otherwise. So we've got 2 minus 1 minus 1. So my two solutions, normally I'd write x equals, but here I'm going to write cos theta equals 1. Or the other answer I get is cos theta equals minus a half. Okay. And then I've got to solve those between 0 and 360. So cos theta equals 1 at 0. Let's think about the graph. And at 360. Cos theta equals minus a half at 120. And then 360 minus that answer, so 240. So those would be our four solutions there. So you can just treat it like a normal quadratic. It doesn't matter that it's cos squared rather than x squared, really. This next one, sine squared theta minus 30 equals a half. Well, we can do exactly the same as what we did before. We could make a substitution. So I'm going to let theta minus 30 equal phi. So now I've got sine squared phi equals 1/2. Square root it. So that means that sine phi is going to be plus or minus 1 over root 2. And then I just treat it as two separate answers. So I've got sine phi is 1 over root 2, or sine phi is minus 1 over root 2. Okay. I should change my limits as well. So that means that theta is phi plus 30. So my limits are 0, phi plus 30, 360, minus 30 from both sides. So this is my new question. between these limits, solving this and this. And I've just got to solve it and then swap it back. So let's do that now. So inverse sine of 1 over root 2 is be 45. And then 180 minus that, 135. And then to get the next pair, 45 plus 360, 405, that's going to be outside my limits. So those are the only two there. If it's negative 1 over root 2, so inverse sine of minus 1 over root 2, and I'll obviously get minus 45 as my first solution, which isn't quite in my limits. We can do 180 minus that answer. It's going to be 225, that is in the solutions. Then we can do 360 plus both of those. So that gives me 315. And 225 plus 360 is going to be too big. And we're not allowed that one. So there's my 4 solutions that I can have within my new limit. And then just swap them back. So theta was phi plus 30. So that means that theta is going to be each of these plus 30. So that's 75, 165, 255, and 345. And those are all within my original limit. So those are my final answers. Let's just have a look at these last two. So tan squared theta equals 2 tan theta. Let's just move it all onto one side. Equals 0. Now I can factorize it. So I can take a tan theta out. Like that. So now I've either got tan theta equals 0 or tan theta equals 2. And then I can solve these between minus 180 and 180. So inverse tan of 0 is 0. And then I can do plus or minus 180. And actually both of those are within my limits. So I got minus 180 and plus 180. Inverse tan of 2 gives me 63.4. And then I can do plus or minus 180. I'm going to do minus first, so that'd be minus 116.6. If I go the other direction, I can get 243.4. That's actually outside my limits, isn't it? So just those solutions there. Question D. 4 sine theta equals tan theta. Let's see what we can do with this one. So we've got a sine and a tan involved, so I can't really go anywhere from here, but let's try and use some identities. So tan I could replace with sine theta over cos theta. Then maybe I'll times both sides by cos theta. And then I think if I subtract sine theta from both sides. Okay, so now I've got something equals 0. I can't really swap the coses or sines for the other type of function because they're not squareds. So that would be, I can't really use sine squared plus cos squared equals 1 here. But what I could do is I could factorize out the sine theta. So I can get to there. So now sine theta is 0 or cos theta is 1/4. And then I can solve both of those between my limits of minus 180 and 180. Let's do that. Sine theta equals 0. It's 0, 180, and minus 180. For the cos part of it, inverse cos of 0.25. 75.5 is my first answer. I could do 360 minus that, but that's going to be too big. So I could do plus or minus 360 from there, but I think those are all going to be too big or outside my range. Yes. So my answers are these ones and just this one here. Okay. A couple more examples of using identities. Maybe I would just, rather than doing the numerical solutions, I might just show you how to get to a point where you can then finish them off, because I think we hopefully know how to solve these numerically now. So let's just think about the identities part. So 2 cos squared x plus 9 sine x equals 3 sine squared x. So I've got sines and coses involved here. Let's try and convert it so it's just sine. So I'm going to try and replace this cos squared. Remember, sine squared plus cos squared is 1. So that means that cos squared is 1 minus sine squared. So that's going to be 2 lots of 1 minus sine squared x plus 9 sine x equals 3 sine squared x. Now I should be able to just rearrange this into a quadratic. So if I put the 0 on the left, then I will have 5 sine squared x minus 9 sine x, and then also minus 2. And then that's just in the form of a quadratic, which you can solve using your calculator. If we do that, that's 5 minus 9 minus 2. So I'll either get sine x equals 2 or sine x equals minus 1/5. Now, a thing to notice here, sine x equals 2, the sine graph only goes up to 1 and minus 1. Sine x equals 2 is up here, so it doesn't actually intersect the graph anywhere. So for that bit, there's no solutions, but for this bit, you could finish it off and find the other solutions here. These ones here, let's do part A. Again, we've got 2 different functions, so we could try and swap them out for the other one. Or I think here we could probably do it with tan instead. So I'm going to make this 5 sine squared theta divided by 4 cos squared theta, and that would equal 1 then. So I'm going to get 5/4 or 5/4 of tan squared theta equals 1. So then tan squared theta is 4/5. And then tan theta is going to be plus or minus 2 over root 5. And you can just treat that as 2 different results and solve them to find theta for both of them. So the one, B. Let's swap the tan theta for sine theta over cos theta. Then I suppose I could times both sides by cos theta. And now I could swap my cos squared theta for a 1 minus sine squared theta. And now I've got a quadratic. Like that. Or I could write it, if you want a positive at the front, sine squared theta plus sine theta minus 1. Okay. If you solve that, you'll then get sine theta equals minus 1 plus root 5 over 2, or sine theta equals minus 1 minus root 5 over 2. And then you could solve those to find theta from there. Okay. If you want something like that, so where you've got sort of a mixture, so you've got some transformed functions, and you've also got some that need identities and so on, then exercise 10F would be the one to do for practice there.